So please welcome Eric and Marie.
So just to take note, first, if I'm looking down at my screen a lot, it's because if I don't, I'm probably going to be looking straight into the spotlight there. So it's not that I don't want to make eye contact with you. I'm really pleased to see all of you here. It's nice, particularly when the topic is assessment, to have such a nice turnout. Nobody's going to throw tomatoes or anything today, I hope. At least not yet. And as our the person introducing us said, my colleague Marie Biankowski is over there, and she will be, throughout this presentation, be adding commentary and examples and elaborating a little bit on what I say, so she'll be jumping in from time to time. And I also just want to emphasize that I don't want this to just be me talking to you. As I go through the presentation, if you have questions, comments, things you would like to add from your own experiences, please just let me know, and I'm happy to stop, and I would, eventually like this to turn into a discussion between us rather than me just going through my slide deck, but we'll see how that goes. As our person introducing us said, we're talking today about supporting assessment practices in secondary computer science education. The focus of our talk today will be on talking about this thing that we call an assessment argument, and we'll unpack what this term means, and as we go through this presentation. Looks like we're still on I need to adjust my...
And while he's doing that, there is we didn't make handouts, but the slides and a handout, we didn't print handouts. The slides and a handout that I'll be talking about a little bit are available for download at that URL. I've been telling people so we don't hit the internet at the same time.
Okay.
So just be ready for that. It's pack.sri.com, and then you'll see the rest of the URL when he gets to that slide.
Thanks, Marie. Yes, I believe I've turned it off the auto advance, so I think I'm in good shape now. And so as part of unpacking this idea of what an assessment argument is, we'll be talking about a framework for assessment design and development that we use at SRI called Evidence-Centered Assessment Design, and a particular part of that, or a tool that is part of that framework, which we call assessment design patterns. And that is actually something that does come, as I will talk in a little bit about, from computer science and other areas. So this will be the focus of our talk today, but as we talk about these general principles in assessment, we will contextualize them and provide examples from work we're doing developing assessments for the Exploring Computer Science curriculum, and so that will provide, I hope, some really tangible examples of these general principles in assessment. As Marie said, we have two handouts that are available on the web address that was on the screen. One is, Marie, do you want to say a little bit about what you...
Sure. Is it okay with the recording if I don't use the microphone? No, it's not?
No, it is.
He's saying it's okay.
Yeah.
All right. So I'll talk slow so people have time to download them. So what we did was we really echoing what was in the presentation, but in a more narrative format, so I could go in a little bit more detail. We really went through and took you kind of by the hand and led you through, led the reader through, here are kind of the way we think about analyzing the domain, pulling out the big ideas, and working all the way down, just as we do in software, all the way down to something that's, quote, executable, which in our case meant we put it on a piece of paper and shipped it out to places like LA Unified in Chicago, and kids wrote nice little notes to us on it. So we kind of get down to the nitty gritty there, but so you can understand it. And then we did a flow chart, because this is a computer science conference, so I said, let's get a flow chart. So we actually have a flow chart in there that's part of this same document that takes you through the decision making that goes on. And the one thing I wasn't able to capture is the iterative nature, but I think Eric will be talking about that. Mm-hmm. So I hope though you find those useful, and if not, I'd love some feedback on it.
And before I continue, I wanted to get a sense of who our audience is. So would you mind raising your hand if you are an ECS teacher? Okay, what about a CS principles teacher? Okay, we have some of those. How about folks that work in professional development? Okay, and what about research? Okay, and what did I miss?
APCS.
APCS, okay. Wow, oh, great, okay.
ECS facilitators.
Okay.
New teachers.
New teachers, great. Okay, fabulous. I'm glad to see we have such a diverse audience. That's really nice. So hopefully, again, I want to, please feel free to stop and ask questions based on your experiences, and also share your experiences in your classroom. So I wanted to start a little bit about with teaching, because a lot of you, as we just found out, a lot of you in here are teachers. And I think that I would argue that there are three main questions that you're interested in asking as a teacher. And those are, what are the main knowledge and skills that students should learn? What classroom activities will help my students or students learn these desired knowledge and skills? And what evidence can I draw from those classroom activities that will help me best determine whether or not the students are learning the desired or the knowledge and skills that I'm targeting with those activities? And when I say activities, I mean a wide array of activities. They could be online, face-to-face, group or individual, in class or homework. And the types of activities that I'm talking about are quite variable. And so in teaching, I think you're really interested in these three central questions. And I would like to point out that in assessment, we're interested in very similar types of questions. It's not a foreign language. It's really very much aligned with the types of questions you are interested in as a teacher, but perhaps at a different grain size or different level of detail. And in assessment, we're really interested in three main questions. And that's, what is the complex constellation or group of knowledge, skills, and other attributes that we should be measuring or assessing? What behaviors or performances should reveal those constructs or give us some kind of evidence about those constructs? And then what kinds of tasks or situations can we develop in an assessment that will elicit those kind of behaviors that count as evidence? And those very much align with the types of questions that you're asking as a teacher. And I just wanted to start with kind of pointing that out to you, that assessment and teaching are very much, I think, aligned with one another and can contribute quite a bit to one another. And in assessment, we call these three questions, or as we begin to make claims and respond to these three questions and build out assessments that are structured around these three questions, we call this the assessment argument. Okay, and the assessment argument is really the kinds of warrants and claims we make as we begin to respond to these three questions and build an assessment. But an assessment argument isn't an assessment. Okay, and there's a lot that goes on between these three general questions that orient us toward kind of making an argument for what an assessment measures and actually developing an assessment. And so how do we get from an assessment argument, which is really organized, again, around making claims and warrants for those claims around those three questions I just shared with you, and get from the assessment argument to an actual assessment? And that's where evidence-centered design comes in. That's how we really move from the assessment argument and those general claims and warrants for those claims that we're making to an actual assessment that we put in front of students. It's how we operationalize or get into the nuts and bolts of designing and developing the assessment. And evidence-centered design was really first developed at Educational Testing Services by Miss Levy, Robert Miss Levy and others in the early 90s, and has since been elaborated on and used quite extensively, not only for design and development at ETS, but also for the development of lots of different tests. And it's a very well-respected framework for assessment design. There are a lot of different flavors of evidence-centered design, just like there's lots of different flavors of ECS, for example. But it does have a basic structure, and I would like to share a little bit and unpack that a little bit for you today. And this is at SRI, at our Center for Technology and Learning, we really focus a lot of our assessment development work around using this framework in various capacities for developing our assessment. And so just generally, evidence-centered design, ECD, I'll refer to it throughout this presentation, is really a framework for assessment design and development. And it views assessment as a process of gathering evidence to support an argument, so back to the assessment argument, about what a student knows and can do. It also provides a structure for an approach that incorporates validity evidence into the assessment design process. So you're not looking at validity after the fact to see if you hit the target. You're actually building the target in a valid manner, and an evidence-centered design really provides you with the structure to do that. It also helps you importantly, document the decisions that have been made with regard to the assessment and the justifications for those decisions. And we often talk about ECD having 5 layers. Okay, and these 5 layers are up here, and they start with domain analysis on the top. They move through domain modeling, conceptual assessment framework, assessment implementation, and assessment delivery. And I'm going to talk about each of these in a little bit more detail, but today we're going to be focusing only on the top 2 levels. We really want you to just understand that ECD is quite an involved framework with lots of different layers, but today we're going to be focusing on the top 2 layers. So the first layer is what we call domain analysis, and that's really where we're interested in I would say 3 primary questions, and that what is important about the domain, and I'm talking generally here, and then I will contextualize this within exploring computer science and how this manifests in the work we're doing with developing assessments for exploring computer science. But just generally speaking, we want to know about what is it that's important in a domain that we want to be measuring, whether that's in math or science or computer science. What is important about that domain that we should be measuring? What are the kinds of work and situations are central in this domain? So what kinds of things, really are tangible in this domain? What kinds of tasks do students engage in, teachers engage in? What kinds of tasks do professionals engage in this domain? And then what kinds of what we call knowledge representations are central to this domain? So what kinds of, how do students and teachers and professionals think in this domain? What kinds of representations do they use to display that thinking? And so that's what when we first start designing an assessment, we want to do a domain analysis. We want to understand what are all the different pieces that are important in this domain that we might want to measure. And then as we move down one layer in ECD, we really move from understanding the domain kind of writ large and understanding all the different pieces to starting to model that domain in a specific way that's amenable to developing assessments. Because in a domain analysis, we have lots of information, but we need to be able to model that in a particular way to develop an assessment. And so we want to really know how do we represent the key aspects of the domain in terms of the assessment argument. So in terms of those 3 questions I shared, this is where we take all the information that we get about a domain and we start fitting it into those 3 questions. We start structuring it in a particular way. And then for the next 3 layers, we call the next layer the conceptual assessment framework, and that's where we move from a general model of the domain, not the nuts and bolts, but just a general narrative model of the domain, to kind of the nuts and bolts. So we might have design structures, and we have in evidence-centered design we talk about the student, evidence, and task models. And the student model is essentially what we want the students to know. The evidence model is what kinds of behaviors will count as evidence towards those targets and what we want students to know. And the task model is the types of things that are going to elicit those behaviors. So again, going back to the assessment argument, and in the conceptual assessment framework, we really start to specify the details of those pieces. And then in assessment implementation and assessment delivery, we really move into things like authoring tasks. We talk about scoring details, scoring rubrics. We talk about statistical models for building evidence of student performance. And then in assessment delivery, we finally have students interacting with the tasks, and we are able to do the data analysis and score analysis. So those are the 5 layers of ECD. But for today, we really want to focus in on the top 2 layers and share with you what we've done in the PAC project developing assessments for ECS in terms of domain analysis and domain modeling. And so we'll start with domain analysis. And in the domain for ECS, we were really interested in computational thinking practices. And I think a lot of you in this room are probably familiar with the concept of computational thinking, perhaps not the idea of practices, but we'll unpack that concept just a little bit. And so we were asking ourselves, again, 3 questions about this domain, about the computational thinking domain. What was important in this domain, in the computational thinking practices domain? What work and situations are central to that domain? And what kinds of knowledge representations are central to that domain? So we were really interested in, when we were looking at computational thinking, what kinds of things really matter in this domain, and how can we make sense of this domain in terms of starting to think about what we should be measuring and what students should know and be able to do. Now, when you're doing a domain analysis, you really draw on lots of different types of resources. And in the case of PACT, where we were developing, again, assessments for the Exploring Computer Science assessment, and the scope of our work, curriculum, excuse me, the scope of our work was to develop assessments for units 1 through 4, so end-of-unit assessments, and then also a summative assessment measuring the kind of core knowledge from those foundational 4 units. That was the scope of our work. And so when we engaged in our domain analysis, we were looking at both lots of different sources of literature, from ranging from the National Academies report, going into 6E journals, CSTA, Journal of Computing and Higher Education, Educational Researcher, and then kind of also not folk knowledge, but Jeanette Wing's well-cited definition of computational thinking, and the National Academy's workshop on pedagogical aspects of computational thinking. We looked at all of these resources, but in addition to that, it's not just the literature, but it's also standards and curriculum provide really important information for a domain analysis. So we looked at both the CSTA standards, we looked at Exploring Computer Science, obviously, and the kinds of learning objectives and practices that were a focus of that curriculum. We also looked at APCS, the big ideas and key concepts and supporting concepts. And then we also looked at next generation science standards and the Common Core State standards, because they also bring in notions of computational thinking, particularly with regard to math. So we were looking across all of these documents to try to figure out what are all the different parts of this domain, and what should we be measuring? What should we be saying students should know and be able to do when it comes to computational thinking? And one of the we began to notice that really practices were central to a lot of the language and information that we were looking at, and particularly in some of the new high school curricula, Exploring Computer Science and CS Principles, they really emphasize this idea of not just computational thinking, but computational thinking practices. And we thought that concept of practices was a really important one to be measuring, and practices really moves us away from just this idea of conceptual knowledge. It really moves us toward, it's not just what goes on in a student's head, but it's the ways they should be able to, the ways of being and doing that students should demonstrate when learning and exhibiting these skills. So it's not just conceptual knowledge, not just traditional conceptual knowledge that you might measure with a multiple choice assessment, but we really wanted to engage students in being able to apply these concepts in different manner, in different ways. And as I mentioned, I just want to put a shout out to, we also noticed in our work with we were looking at the standards as part of our domain analysis, that both the Common Core State standards and the Next Generation Science standards included standards that are relevant and call out computational thinking explicitly. In the Next Generation Science standards, they describe using mathematical and computational thinking as an essential practice for modeling and analyzing and interpreting data. And so I just want to say that, a lot of computational thinking is even getting a kind of a foothold in some of these these very contemporary standards that a lot of states are increasingly beholden to, or at least trying to adopt at some level. Some are not. And so I wanted to talk a little bit about how we started to make sense of all this information that we were looking at in the domain analysis for computational thinking. And so first, as I just said, there's computer science concepts. That must be a part of this domain analysis, and we really needed to include that in our conceptualization of these computational thinking practices. And so if we throw, from these documents that we were looking at in these different resources, we kind of identified many different concepts that were part of this domain, but an example of some of the ones that were kind of central and kept coming up again and again are algorithms, programming, recursion, abstraction, debugging and testing, variables, and there's many more. This is just an example of some of the concepts that we saw as we looked across these different resources. But in addition to computer science concepts, we also saw, and I think this is where this idea of practices starts to really kind of become more apparent, is this idea of inquiry skills. A big focus in science education in the past decade has been the integration of inquiry into traditional science curricula. And I would argue it's no different in computer science curriculum, especially the new ones being developed for the high school space, so that there's a real focus on engaging students in inquiry. So how do they apply their computer science, conceptual knowledge in different ways? And so, in some of these inquiry skills that I'm talking about are things like evaluation, exploration, analyze, explain, elaborate, model, and there's a lot of other types of inquiry skills that you could call out here. But these are some of the central ones that we kept coming up during our domain analysis. And they're explicitly called out in exploring computer science. They have the five Roger Bybee's 5 E's, and those are called out as the focal inquiry skills in exploring computer science, and I know there's others as well. And so we have computer science concepts and we have inquiry skills, but we weren't done yet. Another piece of this of our domain was what we call non-cognitive skills, okay? And so we saw this coming up again and again in looking at these different resources. And by non-cognitive skills, we mean things like communication, teamwork, collaboration, leadership, self-efficacy, self-determination, and persistence. And those were, please go ahead.
Just to be clear, there's no relationship between what's in each row?
No, not direct. No. These are just, and they're mix and match, and I'll talk about that in a minute. That's actually a really good question. No, they're not meant to be read across. These are meant to be read vertically, and then I'll talk a little bit how we can play with this framework. But thank you. So these are, we really felt that when we looked at these practices and what was being emphasized in the curriculum and the standards, it wasn't just computer science concepts and these inquiry skills, but it was also these things that we called non-cognitive skills, particularly around communication and collaboration, but also around persistence and leadership. They really kept coming up again and again. And so as we look across these and start to blend these three columns, computer science concepts, inquiry skills, and non-cognitive skills, we begin to see how we can build some different computational thinking practices. So for example, one of the computational thinking practices that's called out in both CS principles and in exploring computer science is it's analyze our computational work and the work of others, or just analyzing computational work, both your own and others. And you can think of that as perhaps the conceptual knowledge that you could bring to bear there would be knowledge of algorithms and programs and their structure. You could be, in terms of inquiry, you could be analyzing those algorithms, and that's directly called out in the computational thinking practice, but you also might need to be able to explain your analysis and the results of what you're doing and your findings around how you analyze that computational work, both your own or others. And then, again, you're going to need to be able to, you might need to be able to communicate that with others in your classroom, your teacher, or depending on the task, it could be external to the classroom as well. And another example would be another computational thinking practice that is again called out in both CS principles and ECS is collaborate with peers on computing activities. And so again, you could see blending across these columns things like algorithms, programming, and perhaps debugging and testing with things like exploration, explanation, and elaboration. And again, you could have, in this one particularly, you're having students work together and engage in collaboration with respect to exploring, explaining, and elaborating things like algorithms or in the context of debugging or testing. So this is just how I want you to see this is as a general framework for thinking about computational thinking practices. And this is often what can come out of a domain analysis, is lists of concepts and the different parts of the domain that are important and potential relationships between those different concepts or those different pieces. And so from our domain analysis, we were able to extract these concepts and mix and match them in different ways to come up with different computational thinking practices. But we were far from done yet. So we started to make sense of the domain in the manner that I just shared with you, but we were far from having an assessment. And so the next stage was really moving to what we, in evidence-centered design, we call domain modeling. We needed to start to make sense of all this information from our domain analysis in a particular structure, which was around the assessment argument. So those three questions: what do we want students to know? What kinds of evidence will count toward what we want students to know? And what kinds of tasks will elicit that evidence that we need to make claims about what students know? And we needed to structure all of that stuff from the domain analysis in a particular manner. And we do, in evidence-centered design, we do this in domain modeling. And so really, we ask the specific question we ask is, how do we conceptualize and represent key aspects of this domain in terms of an assessment argument? And in evidence-centered design, in the domain modeling stage, the main structure or tool we use for that process is called a design pattern. And what I'm going to do here is I'm going to talk very generally about design patterns, talk very briefly about it in the context of computer science, and then move into talking about it specifically in assessment, because design patterns aren't just used in assessment. In fact, they're used in a lot of different areas. And so you can think of a design pattern as a solution to a problem that repeatedly occurs in our environment, just generally speaking. And it's specified at a level of generality that the underlying approach that's specified in the design pattern can be applied across many different situations, but you can use it in a way that you can adapt it to particulars of each situation. So it's specified at a certain level that it allows it to be adaptable as you apply it in different contexts. And it also, these design patterns often show general relationships and interactions without specifying details. So again, a thing about a design pattern, just generally speaking, is it is specified at a certain level of detail. And it's fairly general and fairly high. It's a high-level representation, a high-level knowledge representation, if you will. Now, in computer science, I'll back up. In evidence-centered design, when we were when Bob Mislevy and others at ETS were thinking about developing design patterns, they looked to three different areas to kind of get the idea. One was architecture, another one was English language arts, where it was used particularly in development of plays, and high-level like storyboarding for plays, and then also in computer science. And so from these three areas, we essentially adapted this notion of design patterns for evidence-centered assessment design in the world of educational assessment. And so and all of you in this room probably know more about design patterns if they're still used in computer science than I do, but in computer science, and particularly in software engineering, design patterns really help programmers tackle complex problems that recur in different guises. And they really provide structured insights into conceptual problem solutions above the level of particular programming languages and implementation environments. So when, I think many of you in here know, when you're working on programming a solution to a problem, you don't just jump into programming. You often conceptualize what the problem is and figure out what kinds of languages and structures are going to help you solve that problem before you start programming anything. And that is what a design pattern essentially serves. That's the role it serves, is it allows you to conceptualize the problem and a solution to that problem at a higher level of detail and at a specific level of detail before you jump into a solution to that problem. Now, in the context of domain modeling, assessment domain modeling, We talk about design patterns as specifying and organizing the assessment argument in a narrative form based on information from the domain analysis. So again, we're taking all of that information that we get in a domain analysis, and we're starting to put it into some sort of structure that allows us to develop and make sense of this information in terms of an assessment. And it's really it's a high-level representation of the assessment argument, and it really represents, again, just like I said in software engineering, it represents a transition point between kind of specialized knowledge about the domain that you get from a domain analysis and the specialized knowledge and the more technical machinery of an assessment. So when you start to involve task designers and psychometricians and other folks, this is an in-between stage where you're building a document or a design pattern that allows you to talk about important aspects of the assessment to different audiences. And that was really one of the motivations for design patterns, is to be able to kind of have an interstitial document that allows different assessment stakeholders. And there's there's content experts, there's teachers, there's psychometricians, there's researchers, methodologists of different sorts. There's lots of people that come together to develop assessments. And this document is really, its role is to allow those different audiences to talk about what we want to measure and how we might want to measure at a particular level of detail before you start implementing specific, in specific contexts and developing certain kinds of tasks and designing certain kinds of evidence models or psychometric models. And they really lay out a design space, particularly for developers, assessment developers, to think about choices that can be made and the connections between those different choices, coherence and trade-offs. So really, again, it serves as a design document at a fairly high level of inference. And as I've said before, the attributes in a design pattern really are meant to structure and reflect the assessment argument. And it can really improve both efficiency in assessment design and particularly assessment development and validity. As I said before, by structuring and kind of putting your domain analysis into this design pattern structure, you're really able to you're starting to build an argument for the validity of assessment. You're starting to make claims about what you want students to know and how you want to measure it, and you're starting to think of the kinds of warrants that will back up those claims that you're making as you respond to the assessment argument questions. But it also improves efficiency because you have this high-level document that can be used across the different assessment stakeholder groups that are working on developing this assessment, and it can really lead to some really, I think, constructive discussions before you get down into the weeds of actually developing the assessment items. And that can improve efficiency by not having to continually go back and go back and go back, that you're doing a lot of planning before you get down into designing the assessment tasks. And if it's not clear already, developing design patterns is an iterative and interdisciplinary process. It not only helps the different assessment stakeholder groups talk, but it requires, ideally, those different stakeholder groups to come together to develop them. And so, you have folks like content experts you've probably already tapped in your domain analysis, but you can continue to use them when you're talking about developing a design pattern and you begin modeling the domain. You have educators, of course, we want teachers involved, assessment experts and methodologists, and practitioners from industry are often good to bring in so they can talk a little bit about industry trends and what's desired in industry. And as I've already said, you really draw from multiple sources of information, including education research, curriculum examples, standards, industry trends, and other documents. So design patterns, the take-home message is that it's an iterative process. You usually have to go through several different iterations to get them specified at a good level of detail for your work, and it really requires an interdisciplinary team to get a fully fleshed out design pattern. It really helps to have multiple people coming to the table. Was there a question? Okay. So I wanted to, in the next couple of slides, I want to talk generally about the structure of a design pattern and what we call the different attributes that are specified in a design pattern, just generally. And then I'm going to give you a specific example of how that plays out in the context of our work. So design patterns start with an overview, and that really is a description of the construct being modeled in design pattern. And by construct, we really mean, again, this constellation of knowledge, skills, and attributes. It's not just computer science concept knowledge. It's really that blended with inquiry skills and non-cognitive skills. That's what we think of, at least in the case of computer science, as a construct. It's what we want to be measuring. And it really is a description. The overview is a description of that. And in the case of exploring computer science, as I will show, the overview is really a description of the focus of a particular unit. And then in the case of our summative assessment, it's a description of the different constructs that we want to measure across those units. But the central part of a design pattern, and what everything else in a design pattern hinges on, is what we call focal knowledge, skills, and attributes, or what we call focal KSAs. And those are the primary knowledge, skills, and attributes. And we don't use the word abilities. That's a loaded term, and we try to stay away from it. Targeted by the design pattern. What do we want to make inferences about? What do we want to be measuring? And so when you think back to the assessment argument and that first question, what constellation or complex of knowledge, skills, and other things do we want students to know? This is where we start to specify those. And you can, when you're thinking of when you're thinking of curriculum, and I'll show this in a minute, learning objectives in a curriculum are similar to focal KSAs in a design pattern. They might be specified at different levels of detail, but it's really what do you want students to know? And when you're implementing an assessment, what are you trying to measure? And a lot of the other aspects of a design pattern kind of hinge on those. So when you start developing a design pattern, you often start with the overview, and then from that you derive the knowledge, skills, and other attributes that you want to be measuring. But then in addition to that, another part of that first question in the assessment argument, what do you want your students to know, are what we call additional knowledge, skills, and attributes. They're not things that are central to what you're trying to measure, but they are necessary for successful performance. So, for example, one of the things that we've discovered in our assessments for exploring computer science is we have scenario-based assessment tasks. So we lay out a scenario for students, and in that scenario, we have multiple embedded items that lead them through a certain structure. And some of the tasks, not all of them, require a reasonable amount of reading skill. We try not to put a heavy burden on reading, but it is an additional skill that students need to bring to the table to be able to engage and engage in the focal knowledge, skills, and attributes that we want. And there are many other additional KSAs that you can specify that are related to focal KSAs, and they really help you understand and be able to separate what's the focus of your measurement for the assessment, but what are other things that you might in particular need to scaffold for students in order for them to be able to engage in the task that measures those focal KSAs. And then there's 4 other attributes that are really central to design patterns. There are others, but these are the focal ones that I want to share today. The two next pieces are what we call potential observations and potential work products. And notice the language. We use potential on purpose because the list we come up with in these design patterns isn't set in stone. These are potential, these are what we believe will help us measure the focal KSAs, but we often, until we conduct a validation study, we don't know if what we're specifying in the assessment argument, or this part of the assessment argument, is accurate. So we call them potential because it's not only to give the notion that there's a lot of different options here, but that they can be refined after we start to collect validity evidence and pilot the assessment. So for potential observations, remember the second question that we ask in the assessment argument are what are the behaviors that are going to provide us evidence for what we believe students should know and be able to do. Potential observations, the attribute in a design pattern, are the way we think about them are features of things that students say, do, or make that constitute the evidence. It isn't what students do or make, it's features of those things that we extract as evidence. So we often talk about them coupled with potential work products because they're very closely related, and it's important to understand the difference between the two. The potential work products are what students actually know, what students actually do and produce. It's the artifact or the explanation, or what they actually do on the assessment. In a portfolio, it might be an artifact. In an assessment, it might be an explanation that they provide. That's the thing they actually produce. That's the work product. The potential observation is what we see in that work product that counts as evidence. And sometimes even in our work, we often confuse the two because they're so closely related, but there's an important difference between the two. And in terms of assessment development, the assessment tasks are often structured around both of them, but the scoring rubric is often structured around the potential observations, and I'll show that in a couple minutes. And then the two other attributes of design patterns that are important to talk about here are things we call characteristic features and variable features. And characteristic features are aspects of assessment situations that are likely to evoke the desired evidence. So they're things that all assessment tasks that measure a particular set of focal KSAs have in common. So when we make an argument for, or we specify characteristic features, we want to say that all assessment tasks that measure the focal KSAs in this design pattern, or a set of the focal KSAs in the design pattern, and I'll talk about that in a minute, what should all of those tasks have in common? And I'll give an example of this in terms of a particular assessment task in a few minutes. The variable features, as the name kind of implies, are the things that you might vary in an assessment task in order to shift difficulty of the assessment task or emphasis on particular content or other, you might vary emphasis of particular content over other content. And so those are things that you might vary across tasks to make some tasks easier than others, or harder than others, and some tasks to measure particular content and over other content that you might be able to measure. So if you have a group of focal KSAs, for example, in a design pattern, you might have some tasks targeting particular focal KSAs in that list, but not all of them. And I'll unpack this in a specific example. But you might then other tasks in an assessment might measure other focal KSAs in that design pattern. And you can vary those tasks. The variable features allow you to specify the things that you might vary in those tasks to measure different sets of focal KSAs. So it's both about difficulty and about emphasis on different content. So this is where I want to transition. So we've talked a little bit about domain analysis generally in assessment. We've talked about domain analysis in terms of, I'll give you a little flavor of what that looked like in the PACT project. And then I talked a little bit generally about domain modeling, how we start to structure that information from our domain analysis. And then how design patterns are a tool that help us do that. And now I want to give you a sense of how we, in the PACT project, how we started to unpack the computational thinking practices and model them in terms of a design pattern. So in our project, we developed two types of design patterns. We developed 6 design patterns for computational thinking practices, not specific to a curriculum, but that are in common to a lot of different, that are in common, for example, to both ECS and CSP, but also found in our overall domain analysis across different resources. And those 6 are I'll give you an example of a few. Analyze the effects of development and computing, design and apply abstractions and models, analyze computational work, which I talked a little bit about earlier, and then collaborate with peers on computing activities. So it's just an example of some of those 6 computational thinking practices. And again, these aren't specific to a curriculum, they're more general, and they were specified at that more general level of detail. But we also, we learned, how should I say this? Through a process of discovery, okay. Yes, Gail and Joanna. It's appropriate that you laugh at that. We also really kind of landed on, those aren't going to help us with regard to ECS. So what we really did then is took our general design patterns and the focal KSAs that were specified in those general design patterns, and we began to map those onto the learning objectives that were specified in the ECS curriculum for each unit, for units 1 through 4. And through that process, we developed design patterns for those first 4 units, in addition to the 6 general computational thinking practice design patterns. And for those of you that know ECS, it was human-computer interaction, problem solving, web design, and introduction to programming. So we have design patterns for those 4 units. But not surprisingly, there is a relationship between our general computational thinking practice design patterns and our ECS units, because we used our general design patterns for computational thinking practices to inform the development of our ECS design patterns, ECS-specific design patterns. So this just shows a little bit of the relationship between the two. So for example, in Unit 1 of ECS, it aligned very, very well. Many of the learning objectives in ECS Unit 1 really aligned well with the focal KSAs that we were specifying for analyzing the effects of developments in computing, which was one of our general computational thinking practices that we identified and built a design pattern for. And there's other relationships here, and this isn't a one-to-one correspondence. For example, the computational thinking practice of designing and implementing creative solutions and artifacts, that really stretched across several of the units in ECS, and that we were happy to see that, because the way that ECS is developed, a lot of the core practices and concepts are spiraled throughout the curriculum. And so we really were happy to see that a lot of these practices were represented in many of the different units. Now, just to start to drill down a little bit more, to show this alignment before I move into a specific design pattern, is for Unit 1, for example, I said that it aligned well with the practice of analyzing the effects of developments in computing. And in the 2 columns I have here, I have example focal, again, remember focal KSAs is focal knowledge, skills, and attributes. And that's what we want students to know. Or in the general case of, if that's particular to a curriculum, we might want anybody that we're designing assessments for, could be adults, to know for the computational thinking practices that aren't specific to a curriculum. But you can see the alignment that students are in ECS. We want students to be able to explain why an object is or is not a computer. But in our the general practice that we really are interested in, not specific to a curriculum, and notice that it's stated a little bit differently, because we might, in our general ones on the far, I guess it's far left here for you, or excuse me, the far right for you, might be not just students, it might be adults or other audiences for these skills, is the ability to describe characteristics of a computer. So there's relationships between the focal. This is just to show that there's relationships for a particular computational thinking practice and ECS unit between the focal KSAs, and this was part of our design structure. And so we moved from these focal KSAs to these, and we also have a document that shows the alignment between the focal KSAs for the units in ECS and the specified learning objectives in each unit. And so what I want to do here is, for a particular design pattern for Unit 1, human-computer interaction, I want to show a little bit about what a design pattern might look like. And this is just as an illustration. It's not meant to be comprehensive. And so in the case for the overview, which is the first attribute of a design pattern, for the ECS design patterns, we really took the overview from the curriculum, because that's specified in a general way what students should know and what they want students to know after they engage in this unit. And I won't read, some of the things in there are they're introduced to major components of a computer, input, output, memory, storage. They consider internet elements or how they're organized. They get fundamental notions of human-computer interactions. They understand what intelligent machine behavior is. They learn characteristics that make certain tasks easier or difficult for computers, so on and so forth. Now, here's an example of some of the focal knowledge, skills, and attributes that we specified for Unit 1. And again, this is a combination of looking from our general design patterns for computational thinking practices and the learning objectives in Unit 1 and kind of blending the two. And this is an example of the focal KSAs we came up with. To give you an idea, this is 3 focal KSAs out of 18. So for the Unit 1 design pattern, we actually defined 18 focal KSAs, and this is just an example of 3 of them. For any given design pattern, and it really can vary quite widely, but generally on average, we have, probably anywhere from 5 to 15 focal KSAs, just to give you an idea, and they can be more than that and they can be less. It just really depends on kind of the breadth of the construct or in this case, the unit that you're trying to specify what you want students to know. And so some of these students are able to explain why an object is or is not a computer. They're able to evaluate the implications of a form of data exchange on social interactions, and they're able to explain how computing innovation has led to new types of legal and ethical concerns. And note the focus on explanation. We're really wanting students, we don't want students to just be able to look at a multiple choice item and say, A describes a computer best. We want them to be able to engage in explanation and reflection and provide evidence in their explanation of what a computer might be, and I'll show this in a minute. And so one of the really important things about design patterns that I don't believe I've made clear yet is in a design pattern, when we develop them, we explicitly specify relationships between the focal KSAs, which we consider to be the anchor in the design pattern, and the other attributes. So we have a system called PADI, and we house a lot of our, it's principled assessment designed for inquiry. We house a lot of our design patterns in this online structure. And in this online structure, you can select, for any given design pattern, you can select a focal KSA, and it will show you the potential observations and work products and variable features and characteristic features that are aligned with that focal KSA. And it's important just to note that that you build in these relationships as you create a design pattern, and it's really important for the designer to be able to see those relationships, to say, given that I want to measure this, here are some evidence some tasks that I can design, and here are some types of evidence that I might want to see in those tasks. And so for the focal KSA, again, this is just for illustration, for the focal KSA, students are able to explain why an object is or is not a computer. Potential work product just basically might be an explanation of why an object is or is not a computer. And potential observations for that work product, so what the kinds of features that you might pull out of that explanation, could be how appropriate the explanation is of why an object is or is not a computer, and appropriateness, well, that's a pretty broad term. It could be things like, did the student correctly identify aspects of the object that relate to aspects of a computer? And did the student correctly identify aspects of a computer that the object that you pick lacks? So those are stated at a general level of detail, but those are the kinds of things you might look for in an explanation that a student provides as to why an object that you pick, could be anything, is or is not a computer. And so they need to understand what are features of a computer, and does the object that you specify in a task to what extent it actually contains those features. In addition,
Eric,
yeah.
I just want to do a time check.
Yeah.
About 10 minutes if we want to have time for questions.
Yeah, no, I got the
Good.
paper in the back,
Okay,
so
great.
I'll try to move through this relatively quickly. Characteristic features for this particular focal KSA could include students are presented with an object. So all tasks should that measure this focal KSA need to present students with at least some object. And the object must have clear characteristics that allow the evaluation of whether or not it's a computer and it contains features similar to a computer. Variable features, things that you could vary in tasks that measure this focal KSA, could be whether or not the object is considered a computer or not, obviously, whether students are able to argue either way if the object is or is not a computer, and the degree to which the important characteristics are explicitly stated in the problem or must be inferred by the test taker. So you might scaffold a particular task to be easier by listing the aspects of the particular object you choose, and then students have to be able to say, oh yes, that computer has that, it doesn't have this, or you could just leave it open-ended and make them understand what those characteristics are themselves, and that's a more difficult task. So in our assessments, we have a task where students have the scenario, again, these are scenario-based tasks. You and your friend are debating whether or not a microwave is a computer. So there you have an object, a microwave, and the student needs to explain why they think a microwave is or is not, they could argue either way, is not a computer. In your response, describe at least 2 characteristics of a computer that support your explanation. Now what I want to show you is how this task that we came up with is related back to the attributes in the design pattern. So here we have the focal KSA is students are able to explain why an object is or is not a computer, and we explicitly ask them to do that. So that's a fairly transparent connection. The potential work product is an explanation. So students need to provide an explanation, and that's the thing they produce in the assessment task. Characteristic feature is the student must be presented with an object. Microwave is the object. And the object must have clear characteristics that allow the evaluation of whether it is a computer. Now, you might argue that not everybody knows. I mean, everybody might not have a microwave, but most people know what a microwave is generally and what a microwave can do. And so we felt that it was okay to use a microwave as a commonly known object. And it had fairly clear characteristics. Now, variable features could be the degree to which important characteristics are explicitly stated. We didn't state any of the characteristics of a microwave. We assumed that students would know enough about a microwave that they would be able to draw out what the characteristics of a microwave are and how they might be related to a computer. Now, assessment responses support that assumption to some extent, and maybe not fully though. And whether or not a student can argue either way that the object is or is not a computer, we allow students to argue either way. Now, a microwave can be considered a computer, but it might not be, and so we allow students to be able to argue either way on that. Now, I said that one of the things I didn't share right there is potential observations. Because really where you see the potential observations manifest in an assessment task is really in the scoring rubric for that task, which specifies the types of evidence that or the features you're going to look for in a task and score. And so our scoring, this is a draft scoring rubric. We're still piloting the assessments. But for this particular task, there's I should have mentioned this earlier, but this is part of a much longer task. There's like 5 different parts to this task. This is the opening of the task, but there's other parts in this. So for this part A of this task, there's 2 points possible. And in the rubric we say the points are given based on the explanation. The explanation should relate what a microwave can do to an aspect or aspects of a computer. And we specified some aspects, what we call defining aspects or characteristics of a computer. Can include things such as reducing human effort, taking inputs, giving outputs, storing data, processing information. And students don't need to use these terms per se, but they need to be able to talk about what a microwave can do in those terms and relate that to a computer. So they get 1 point for listing at least 2 valid aspects of a computer. The response must name specific terms such as input, output, process data, programming. So we actually, that's one thing that we're changing because a lot of students don't necessarily do that. They don't name those concepts, but they do describe what a microwave can do in a way that references those, or you can infer that that's what they're talking about. And then they also get 1 point. It's really important that they don't just name the aspects of what a microwave can do, but they need to relate it to what a computer can do. It's it's not just that they can identify different characteristics of that object. It's that they need to relate it to what the computer can do. And if they only name one aspect and relate it, they only get 1 point. And misconceptions about a microwave and how they work don't count against them. Excuse me. So the potential observation, if you remember, is did the student correctly identify aspects of the object that relate to aspects of a computer? And in our rubric, we actually give them points, and we build evidence around whether or not they do that. So again, this is where the potential observation comes in and helps us structure a rubric around whether or not a student correctly identified aspects of that object and related it to a computer. And just for fun, we in our rubrics we're providing exemplar responses at different scoring levels. So an example 1-point response was when referring to a microwave, it is programmed to heat up or unfreeze food. And so we gave them a point because they're saying that that's saying that it reduces human effort, and they're not explicitly saying that. And one of the challenges in the pilot has been at what level do we draw inferences about student responses? And then an example 2-point response, one that was particularly strong, is a microwave is a computer because it's programmed to help us heat up our food when it is cold. We can also program the time of day to let us know what time it is. So they're using the concept of programming and different uses of the microwave to reduce human effort. Yes?
I'm intrigued by this assessment because it seems heavily biased in favor of the von Neumann definition of a computer as opposed to like Turing definition.
Okay.
Computer.
Marie,
And
as a
it seems like this lesson is heavily about that different people define computers differently.
So Marie, do you want to respond to this as our computer scientist?
I would take it back to the ECS.
Yeah.
We defined it as exploring computer science. It's specific to the curriculum.
Yeah. That's essentially we did. Again, this is, sorry.
Does it specify then in the ECS curriculum specifically how a computer is defined?
No.
That's what I'm saying, so how is
That's the
it?
concern.
Okay.
Right, and this is the first time we're seeing these responses too. So, yeah, it's interesting, because I think this is one of the conversations we had from the beginning, right? Like, what the students' definition of a computer is after they've gone through the course may be different than it is the first day of school, which is sort of when this is happening. So
Right.
That's part of the reason I'm assuming that we're not looking for specific terms all the time either, right? Input, output, et cetera, et cetera.
That's right. And we're also, just to state, we're in our summative assessment, we ask a similar question. So we'll be able to see how their conception of what a computer is changes if it does. But that's a fair question, and it's something that I think we can take into account as we revise these, because it is a pilot at this stage. So, yes.
One thing you haven't said yet is whether there's evidence or response that they give that counts against them. There's this stuff of anti-patterns, design patterns and anti-patterns, things that are bad. And so if they said an aspect of a microwave was like a computer, but that wasn't an aspect of a computer, that just wouldn't count against them. Or there's a logic problem where they say a microwave is not a computer because it heats food up. Computers don't heat food up. Like give it an aspect of a microwave that,
Right.
that's a logic problem. But those here, it looks like that doesn't count against them.
Well, yeah, that's a fair question, and one of the things we're trying to do from the student responses is, we talk about, how close are our inferences about student responses to what they're doing, and what I didn't show here is the long list of responses that don't get scores. So I should have probably brought those, but we have plenty of examples where in terms of when you look at the variability across the student responses we have, that's what we're setting our points to, and so we're trying to give credit for students that are somewhere in the middle, but there's plenty of responses where students just clearly don't have any. It's not just that they don't understand how a microwave works, but they're not identifying characteristics of a microwave that would be related at all to what a computer can do. Yes.
So I wonder, the thing about the misconceptions about the microwave mapping scored against them, I'm wondering if students are told that, and if that might not raise a risk about gaming the system, because you could just coach your
Yeah.
students to jump in and make assumptions that aren't right every time. but that you-
No, they're not told that. We don't tell them that misconception. They don't need to know how a microwave works. No, we don't do that. But no, it's a fair point. Are we out of time?
I'd say in interest of time,